Hey, welcome back. This is test 2 review for Math 1540, which is trig. And so the first thing first, again, in Blackboard in the course content area, I've included the front page of test 2. So you could use that to practice sort of memory dump that you'll have to do on the first page of the test. I'm going to list the identities that I'll require you to put here in this box in a second. Before I do that, I just want to show you that I am giving you a formula sheet this time, so you're not going to have to memorize tons of formulas. So you can either print this out or you can kind of write them down on a piece of paper for you to use. Okay, so these formulas, although they're important, I typically don't use them all that often in Calc 1 and Calc 2 and Calc 3, so I'm not going to force you to memorize them. But that's not to suggest that you will never use them in later classes, especially if you take an engineering. I really am not familiar with all of the trig that's required for engineering classes. So anyways, I'll be giving you this formula for the second test, the formula sheet for the second test. Okay, so which formulas do I need to have memorized then? So let's go ahead and kind of list those. You should have these already memorized from the first test. Okay, so first off, the reciprocal identities. And again, these are just, sine is 1 over cosecant, and then cosecant is 1 over sine. Cosine is 1 all over secant, and then secant is 1 over cosine. Tan is 1 over cotan, and then cotan is 1 all over tan. Okay, then you have the quotient identities. T's. Apparently I missed some of the letters here in this other guy. Okay, tan x is sine x over cosine x, and then cotan x is cosine x over sine x. The Pythagorean identities. You have the first main one, sine squared x plus cosine squared x is equal to 1. Then if you divide everything by cosine squared, you'll end up with tan squared x plus 1 equals secant squared x. And if you divide everything in the first equation by then sine squared, you'll get 1 plus cotan squared x equals cosecant squared x. Then the even and odd identities. Basically, the only ones that are even are going to be cosine and secant. So cosine of negative x is equal to cosine of x. And then secant of negative x is equal to the secant of x. Everybody else is odd. So sine of negative x is negative sine of x. Cosecant of negative x is negative cosecant x. And cotan of negative x is negative cotan x. And then finally, tan of negative x is negative tan x. And then, so all these identities you had memorized for the first test. So this is hopefully just going to reinforce them in your brain. Then the last 3 identities, which are kind of identities that we learned in Chapter 5 here, often pop up again later in Calc 2. So I want to make sure that we have these memorized in particular. Okay, maybe I should make you force memorize more, but this is good enough for me. 2 sine theta, cosine theta. I mean, memorizing math formulas is an art unto itself. They write books on it. So anyways, 1 minus cosine 2 theta over 2, 1 plus cosine of 2 theta over 2. And okay, so those are the formulas that I will want to see on that first page. And basically I'll make it worth like, I don't know, like 10 or 12 points. And every one you get wrong, I'll take off a point. Okay. Okay, so let's dive in then. Of course, on the first page, any other identities you want, you can list. So you can put the reference angles and their functional values as well. I won't grade anything extra you put, so if you get it wrong, I won't take off points. But anyways, let's dive in now. So I'm going to give you the sections and then the types of problems, the sort of pool of questions I'll be taking my problems from. So 5.1 was about verifying identities. And in particular, I'll be looking at problems like 1 to 45 odd. And I'll take probably about 4 or 5 problems in there. And what you're doing is proving the identity. And the way these problems always work is you're kind of, you write starting on the left side or the right side. And then you kind of write the identity and then prove it equals the right side. So starting on the left, we note a bunch of stuff, and then hopefully you end at which is the right side, or vice versa, right? You can start on the right and then end on the left. I'm not going to give you any ones that would be like super hard, where you have to kind of start on the left and then you get stuck and you have to start on the right and then you kind of build the tunnel like I talked about in my videos. I'm not going to give you one that hard, but you should always be using this format for your proofs, okay? So you're always beginning with a sentence and ending with a sentence, and then there's a bunch of math stuff in the middle, okay? Okay, so I'll expect to see that. I don't want to see a bunch of random formulas strewn through the white space on your paper. If it looks like it was randomly kind of thrown together, I'm not going to be happy. So part of your job with these proofs is being able to explain to another person what exactly it is you're showing, So if nobody else can understand what you're doing, it's kind of pointless. It has no value. Okay. So anyways, I expect to see starting on the left or starting on the right, and then you end up with which is the right side or the left side. Okay. Okay. So let's dive right in here. We're verifying identities. Here's number 5. We have tan x, cosecant x, cosine x equals 1. So usually I start on the more complicated side, so there's a right side and a left side. I'm going to start on the right side. So starting on the right, I notice tan x, cosecant x, cosine x equals, and here I'm going to use quotient and reciprocal identities to rewrite this. So tan is the same as sine x over cosine x, cosecant is 1 over sine x, and then cosine is, just cosine. So we can write it as cosine x over 1 if you wish. So the sines cancel, the cosines cancel, and you end up with 1, and that's what we wanted to show. So that's which is well, I started on the wrong side. I said I don't know my left from my right, apparently, guys. I apologize. So starting on the left, right? Starting on the left, I notice all this junk, and I ended up on the right, which is the right side, which is what I wanted to show. And I'm done. Okay. Okay, so there's none of this business where you're trying to solve it like an equation. There should be none of this kind of moving from one side to the other side. No, that's what you do when you're solving equations, and that's not what we're doing here. We're trying to prove something. So prove an equation is true. Okay. When you solve an equation, you've kind of assumed implicitly that first equation is true, and then you're just manipulating it using rules from equations, where you can add something to both sides, subtract something on both sides. So this is different. is kind of what I'm trying to say. All right, anyways, let's look at another one, number 9. So we have cosine squared x minus sine squared x equals 1 minus 2 sine squared x. I think I'll start on the left again. So starting on the left. So you always I want to see that written. Starting on the left, I note cosine squared x minus sine squared x equals. So if you look on the right, you want to end up with something just in terms of sines. So that kind of suggests to me that I should replace cosine squared with using a Pythagorean identity, right? So if you remember, cosine squared plus sine squared is 1, so cosine squared must equal 1 minus sine squared. And then we can, drop the parentheses and combine like terms. We end up with 1 minus 2 sine squared x, and that's the right hand side, which is what I want to show. Okay, let's look at another one. So these are pretty easy so far, just one step. 1 minus cosine theta all over sine of theta. We want to show that's equal to cosecant of theta minus cotan of theta. Okay, so I'm going to start on the left-hand side. Sometimes they abbreviate that LHS. And note what? Well, I have 1 minus cosine theta all over sine theta. And one of our sort of tricks, they give you a bunch of tricks in this section, right? There's like factoring, you can multiply top and bottom by something. You can do in this case, we're going to split it into 2 fractions, right? So the reverse of finding a common denominator and combining everything over a common denominator is you're taking it apart over the common denominator. So you'll end up with 1 over sine theta minus cosine theta over sine theta. And in the videos, I usually call that butterflying, because it kind of looks like you make a butterfly, Okay. Then you can just use your quotient and reciprocal identities to denote that 1 over sine theta is cosecant theta, and then cosine over sine is cotan theta, okay, which is the right-hand side. And I'm done. Okay, so that was another kind of easy one. Okay, let's look at one that's a little harder. So it's like 27. We have tan t plus cosine of t all over 1 plus sine t equals secant t. Okay, so this time I'm going to start on the left, the more complicated side. And the first thing you do is rewrite that left side. Okay, I'm not going to skip a step, even though that may be nice for my hand, so I don't get carpal tunnel. It's bad for the reader. Okay, this kind of, even if I got my left and my right mixed up, the reader could still tell what I meant, because I'm going to write that part again. So starting on the left, I note, and I expect you to do the same. I expect you to first rewrite the side you're starting on. Okay, I have 2 terms. I'm going to end with 1 term. So I think a good idea is to find a common denominator and combine the numerators over the common denominator. So tan of t is the same as tan of t over 1. And then to get a common denominator, I'm going to multiply top and bottom by 1 plus sine t. Okay. And I'm going to rewrite tan as sine over cosine. So just one extra thing. Oops, get my office hours. So I'm going to write this as sine t over cosine t. Okay, and then plus, of course, cosine t all over 1 plus sine t, and then I'm going to have to multiply it on top and bottom by cosine t. And you may wonder, why did I do that? Why did I change tan into sine over cosine? It's just sometimes easier, if everything's in terms of sines and cosines, Those are the more familiar functions. Okay, so usually it makes it easier to spot patterns and identities. Okay, so anyways, in the first fraction, if we distribute the sine t, so it'd be, sine t times 1 plus sine t. You're going to end up with sine t plus sine squared t. And then plus over here, cosine times cosine is cosine squared t, all over the common denominator. Cosine t times 1 plus sine t. And then in the numerator, you can see there's this part, the cosine squared plus sine squared, that's 1 from our Pythagorean identity. So you get sine t plus 1 all over cosine t times 1 plus sine t. And then you see that the sine t plus 1 is the same as 1 plus sine t. That's a common factor in the numerator and denominator. So we can remove that, and we end up with 1 all over cosine t, which is equal to secant t, which, of course, is the right-hand side. Which is what we want to show. Okay. So this one a little bit longer. You may have to spin your wheels a bit, but hopefully you'll get to the same conclusion I do. So there's more than one way to kind of skin a cat often. Okay. And the more complicated there are, the more variations you're going to see. Let's look at kind of one that's a later problem in the set that I've given you. Number 42, we have tan of 2 theta all over, plus cotan theta, plus cotan of 2 theta also, all over secant of 2 theta. And that equals cosecant of 2 theta. Okay. Okay, so again, I'm going to start on the complicated side. So starting on the, in this case, the left-hand side, I note tan of 2 theta plus cotan of 2 theta all over secant of 2 theta. I'm going to rewrite everything in terms of sines and cosines again. Okay, that just makes it easier on me for some reason. So I'll have sine of 2 theta all over cosine of 2 theta plus cosine of 2 theta all over sine of 2 theta all over secant of 2 theta, which is 1 all over cosine of 2 theta. Okay. So I have this huge complex fraction. I can simplify it a little bit by multiplying top and bottom by the cosine of 2 theta. Okay, so if I do that, it's going to clear out that denominator, because you'll end up with cosine 2 theta over cosine 2 theta, which is just 1. And I'll just be left with the numerator, right? So this will equal, after I distribute, so I'm going to distribute. In the first distribution, I get even more cancellation, right? Sine of 2 theta over cosine 2 theta times cosine 2 theta. The cosine 2 theta is canceled, and I'm just left with sine of 2 theta. Plus this guy, I don't have any choice in this one. This one is cosine 2 theta squared all over sine of 2 theta. And then all of this is over 1, but we don't have to write that. That would be silly. Okay, so anyways, we have this thing. We ultimately want to end with one term. So let's combine these terms by finding a common denominator again. So here, sine of 2 theta is the same as sine of 2 theta over 1. And then I'll just multiply top and bottom by sine of 2 theta. I'm going to have to smush this other junk in. So I have cosine 2 theta squared. I'm just putting the square on the outside because of that 2 theta thing. If I put the square on the inside, it just looks crazy. And that's all over sine of 2 theta. Okay. So now we'll have sine squared 2 theta over sine of 2 theta plus cosine squared of 2 theta over sine of 2 theta. So I can combine the numerators. Sine squared 2 theta plus cosine squared 2 theta all over sine 2 theta. And again, that's a Pythagorean identity up top, right? So just because, normally you think of it as cosine squared theta plus sine squared theta equals 1, you can have any angle in here. You can put cosine squared of 16 theta plus sine squared of 16 theta. As long as these are the same, it's always just going to equal 1. Okay. All right, so in the numerator we'll have 1, and the denominator sine of 2 theta. And then the reciprocal identity means that that's cosecant of 2 theta. And if you look back above, oh yeah, that's where I wanted to end up. So that, which is the right-hand side, which is what I wanted to show. Okay, so I'm done. Okay, great. So that first set of problems, we're not using any of the high-powered formulas from the formula sheet that I kind of give you, right? I didn't need any of these crazy formulas. So that's kind of how it'll be in that first set of proofs that I give you. I'm not going to expect you to use anything beyond kind of what you already had memorized from chapter 4. Okay. So I know there's like weird sine 2 theta identities. Sine of 2 theta is 2 cosine theta sine theta. I wouldn't expect you to be using those on this first set. Okay. In 5.2, we get the next set of identities. In particular, I'll be worried about problems 13 to 41. I may give you one identity problem in this section, but these formulas, where are they? These formulas are the top formulas, okay, here on the formula test 2 sheet. The couscous formula is the same sign formula. Okay, so 5.2, let's dive right in. The first question, they want you to evaluate the sine of 105. So that was the magic of these formulas. You can use them to evaluate sort of non-reference angles. And how did we do that? Well, we break it down into a sum of reference angles. So something plus something, such that I can figure out the sine of those somethings. Right. So in particular here, it looks like 60 and 45. So 60 plus 45, of course, is 105. And I know how to take the sine and cosine of 60 as well as the sine and cosine of 45. Okay. So using the same sine formula, what will that be? Sine 60 cosine 45 plus sine 45 cosine 60. And then we have the reference angles memorized from the last test. I expect you to have them still memorized. Please don't use your calculator for these. Sine of 60 is going to be sine of pi over 3, which is root 3 over 2. Cosine of 45 is root 2 over 2. And then plus root 2 over 2 times 1/2. Okay. That'll be root 6 over 4 plus root 2 over 4, which equals root 6 plus root 2 over 4. Okay, let's look at one where we kind of go in the other direction. So problem 29, you have the sine of 5 pi over 12, cosine of pi over 4, minus cosine of 5 pi over 12, sine of pi over 4. Okay, so using the same sine formula, this time we note it's sine of 5 pi over 12 minus pi over 4. Right, so we just use those 4 formulas, but use them in the other direction. So I'm sort of starting on the right side of the last of those 4 formulas, and then going to the left. Okay, and then I should be able to simplify this. Sine of 4 pi, oh, whoops, if I find a common denominator, this will be 3 pi over 12. 5 pi over 12 minus 3 pi over 12 is 2 pi over 12. And then simplifying that, sine of pi over 6. Sine of pi over 6 is just 1/2. Okay, 39, verifying the identity. So I'll probably give you one verifying here, and this will be kind of the last verify the identity. I'm not going to get carried away with the identities. Verify the identity. So here we have sine of alpha plus beta plus sine of alpha minus beta. And we want to show that's equal to 2 sine of alpha cosine beta. Okay. So I'm going to start on the left side. So I expect you to write that out, starting on the left. And then you copy down the left side. So starting on the left, I note sine of alpha plus beta plus sine of alpha minus beta. Then I can use my same sine formula, so I have sine alpha cosine beta plus sine beta cosine alpha plus sine alpha cosine beta minus sine beta cosine alpha. Okay. So I have 1, 2 cosine alpha cosine betas. And then these two are additive opposites, so they cancel out. And lo and behold, I am on the right-hand side, so which is the right, which is what I want to show. Fine. Let's move on then to 5.3. In 5.3, we start getting tons and tons of more identities. In particular, it's this second wedge here on the formula sheet, starting with cosine 2 theta, ending with tan of alpha over 2. But there are those three I kind of have you memorized that you have to use. Okay, so from the top, the ones that you need to have memorized that aren't on the formula sheet were these. These also came up in that section. And note, from these two formulas, you can get sine of theta over 2 is equal to negative plus or minus square root of 1 minus cosine of theta over 2. And then from this formula, you get that cosine of theta over 2 is equal to plus or minus square root of 1 plus cosine of theta over 2. So you may want to write those down on your first page for reference, because it's not on the formula sheet and you will have to use them. Okay, so let's go back there. Where are we? 5.3. So 5.3 problems, I'm thinking 7 to 13, and then 55 and 57. Okay. So in that first section, let's look at number 9. We expect you to figure out the sine of 2 theta, part B, the cosine of 2 theta, and then part C, the tan of 2 theta. Okay. So to figure these out, you kind of need to know what cosine of theta and then sine of theta are. You can't like do some multiple of 2 and have the answer. So they give you some information to start off with. So cosine of theta, they're going to tell you is 24 over 25. And they tell you that theta is in the 4th quadrant. Okay. So what you want to do is draw your triangle in the 4th quadrant. So here's my 4th quadrant. It's a right triangle. Here's theta. Cosine is adjacent over hypotenuse, and then you use Pythagorean theorem to get the 3rd side. So we have 24 squared plus b squared is 25 squared. B squared is 25 squared minus 24 squared. If you plop that in your calculator, you'll get 49. And then, of course, b is plus or minus root 49, which is 7. So this is either plus or minus 7. Because it's in the 4th quadrant, it has to be negative 7. Okay, so part A, sine of 2 theta. So you want to convert this into sine in terms of trig functions that have just theta in them. Okay, so if you remember back to those 3 formulas at the top of the page, it's the first formula. Sine of 2 theta is 2 sine theta cosine theta. So sine of 2 theta is 2 sine theta cosine theta. And then we can substitute in, right? So 2 sine of theta using the triangle is opposite negative 7 all over hypotenuse, 25. And then cosine theta is given, 24 over 25. Multiplying that all out, you get negative 336 all over 625. Okay. Part B, cosine of 2 theta. Okay, this isn't one we have memorized. It's not going to be one of those guys. It's one on the formula sheet. So this first formula and this cosine 2 theta is cosine squared minus sine squared. Sine squared theta minus sine squared theta. Okay, and then you just plug and chug. So we're looking at 24 25ths squared minus negative 7 25ths squared. And if you plug that into your calculator, you'll get 527 all over 625. Okay. Part C, tan of 2 theta then. Going back to our formula sheet, tan 2 theta is 2 tan theta over 1 minus tan squared theta. minus tan squared theta. Okay. So now we need tangent. So tangent is opposite over adjacent. So negative 7 over 24. All over 1 minus negative 7 over 24 squared. Okay. Let's see. This will be negative 7 over 12 all over this thing. If you put that in your calculator, you should get 527 all over 576. And that will be negative 7/12 times 576 over 527. And then if you multiply that out, you'll end up with negative 336 over 527, okay, which is your answer. Okay. So that's the first set, and then the second set are the ones associated with these root formulas here and here. And the trick was this: you have to know what quadrant theta over 2 is in order to use the formula. So if theta over 2 is in the first quadrant, you use the positive. If theta over 2 is in the second quadrant, you use the negative. Okay, and same for cosine. Oh, well, wait. If theta over 2 is in either the first or second quadrant, it's automatically positive for sine. If it's in the third or fourth quadrant, it's automatically, you have to use the negative. Okay. For cosine, if it's in the first or fourth quadrant, it's positive, but if it's in the second or third quadrant, it'll go negative. Okay, okay, so let's take a look at the actual problem then. This is now number 57. They want to know what is A, the sine of alpha over 2, B, what is the cosine of alpha over 2, and then C, what is the tan of alpha over 2. So they give you some information. The secant of alpha is negative 13 over 5. Alpha itself is in between pi over 2 and pi. So we need to know what alpha over 2 is in between in order to figure out whether it's plus or minus. So what I do is multiply everything by 1/2, and you get pi over 4 less than alpha over 2 less than pi over 2. So alpha over 2 is in the first quadrant. You know, it's from pi over 4 to pi over 2. It's in here somewhere, which means you're using the plus version on the roots. Okay. Okay. So, anyways, let's go ahead and draw what we're dealing with. The secant alpha, that part of it, is then in the it's going to be in the second quadrant. Alpha is in the second quadrant. Alpha over 2 is in the first quadrant, though. So it's in between pi over 2 and pi. So our triangle will be over here in the second quadrant. Here is alpha. Sorry, I butchered that letter. And then it's a right triangle. And secant is hypotenuse all over adjacent, where this has to be negative 5. And then the right, using Pythagorean theorem, we'll have 25 plus b squared is 169. So b squared is 144, and so b is plus or minus 12. Because it's in the second quadrant, the y value must be positive. So it's 5, 12, 13. Okay, so now part A. Sine of alpha over 2. Okay, so we're using this positive square root of 1 minus cosine of alpha all over 2. Okay. So cosine of alpha is, so cosine is adjacent over hypotenuse. So we're going negative 5 over 13 over 2. So this will be the square root of 13 over 13 plus 5 over 13 is 18 over 13 divided by 2 is the same as multiplying by 1/2. So this will be the square root of 9 over 13, which is 3 over root 13. You don't have to rationalize the denominator. Let's leave it like that for me. Next, cosine of alpha over 2. Again, you're using, because alpha over 2 is in between pi over 4 and pi over 2, you're in the first quadrant, so you use a positive square root. And this time it's 1 plus cosine alpha over 2. So that'll be 1 plus negative 5/13 over 2. which will equal the square root of 13 thirteenths minus 5 thirteenths is 8 thirteenths. Divided by 2 is the same as multiplying by 1/2. You'll get radical 4 over 13ths will be 2 over radical 13. Okay. Part C, tan of alpha over 2. You can go back, there's a tan formula given in the formula sheet, but you could just note that that's the same as sine of alpha over 2 all over cosine of alpha over 2, which you already have the answers for, right? So that's equal to, I guess, 3/2. If you just take 3 over root 13 divided by 2 over root 13, that's the same as 3 over root 13 times root 13 over 2. The root 13s cancel, and you get 3/2. Okay. Okay. So hopefully that won't be all that tough. Let's look at 5.4. So now we get the last set of equations on our formula sheet. There's these 4, and then these other 4. The other 4 are kind of no, this is it. These are the ones we need. Okay, so let's dive in here for 5.4. We're looking at problems like 1 to 21 in the book. So first we want to express this as a sum or a difference. So they're going to give you a product, and you want to express it as a sum or a difference, and then simplify if possible. Okay. So number 5, we have sine of x cosine of 2x. Okay. So you just go to your formula sheet and find that thing, sine cosine formula. It's this third formula here. So you get 1/2 sine plus sine. So 1/2 sine of x plus 2x is 3x, plus sine of x minus 2x is minus x. Okay, now I would expect you to simplify that using your odd and even formulas. So this would be 1/2 times sine of 3x, and then that would be minus 1/2 times sine of just x. Okay? Because sine of negative x is negative sine x, and then when you distribute the 1/2, you get that expression. Okay, going in the other sort of direction, you're going to take a sum and express it as a product. Okay, so we're looking at number 19, something like that. Sine of 75 plus sine of 15 equals. So, looking at my formula sheet, it looks like this formula here, this first formula and the second set. So this will be sine of, I've forgotten the formula already. So where's the formula sheet? Sine, no, it begins with a 2, right? So it's 2 sine of alpha plus beta, 75 plus 15, 85, 90 over 2 is 45. And then cosine of 75 minus 15 is 60 over 2 is then 30. Okay. I think that's it. Yeah. And then we're going to evaluate those without a calculator. Root 2 over 2 times cosine of 30 is root 3 over 2. So we end up with one of the 2's canceling, root 6 over 2. Okay. Okay, the last problems then are solving equations. So you have the infinite solution types, and then the ones that are on the interval from 0 to 2 pi. Let's dive right in there. A big range of problems, 11 to 73, so all kinds of types. Solving trigonometric equations. So let's look at this first one, and we're looking for all solutions. So 4 sine of theta minus 1 equals 2 sine theta. So what we want to do is isolate the trig function on one side. So if I subtract the 2 sine theta, I get 2 sine theta minus 1 is 0. And then I could solve this for sine. So sine theta equals 1, and then sine of theta equals 1/2. Okay, so the deal with this is you get the solutions in between 0 and 2 pi, and then you tack on 2 pi n, right? So the first solution for 1/2 is the pi over 6 in the first quadrant. So you'd have pi over 6 and then plus 2 pi n, right? The second set of solutions where sine is also positive, that's the second quadrant, so it'll be this angle, which is 5 pi over 6 plus 2 pi n. Okay? And then these would represent all your solutions. Okay, let's look at another one. The next set of problems I want to look at are just purely on the interval from 0 to 2 pi, but expect these ones where you have to write out your answer in terms of infinite solutions. Okay, we need to know how to do that. But anyways, these next ones are on the interval from 0 to 2 pi. Okay, so 29, tan of 3x equals root 3 over 3. Okay, so you may want to have that, do the reference chart, you know, the 0, pi over 4, pi over 0, pi over 6, pi over 4, pi over 3, pi over 2, and then list sine, cosine, and tan for all those on that first page. But anyways, these multiple angle problems, you kind of almost have to write the infinite solutions anyways, right? So you're going to have, if you think about the unit circle, the reference angle is pi over 6, yeah. Because tan of pi over 6 is 1 over root 3, which is root 3. Okay. So you're going to have 3x equals pi over 6 plus 2 pi n. And then also 3x, or 3x equals, and let me not do this below. Let me do it to the side. Or 3x equals, the other one is in this quadrant, so 3x equals, what is that, 6 pi over 6, 7 pi over 6 plus 2 pi n. And because of the symmetry with the tan function, you can combine these into one. 3x equals pi over 6 plus pi n, because you can just move by pi to get to here. In other words, you can reduce this set of things by just kind of simplifying it into one expression here. Okay, so anyways, when you're on 0 to 2 pi and you have one of these multiple angle things, you kind of still have to give me the infinite solution cases, because when you multiply by 3, it's going to make the angle kind of smaller. So you're going to get more solutions in between 0 and 2 pi than you normally would. So you're going to need to make these guys. So anyways, the first thing you do is multiply everything by 1/3. So you get x equals pi over 18 plus pi n over 3. And to make life easier, I'm just going to get a common denominator here. Pi over 18 plus 6 pi n over 18. Okay. And then you're just, you go x1 is pi over 18. Okay. And then x2 is pi over 18 plus 6 pi over 18. So that's where the n is 1. Okay, so this will be 7 pi over 18. And you keep doing this until you get something that's bigger than 36 pi over 18. In other words, 2 pi. Right? So x3 is going to be pi over 18 plus 2 times 6 pi over 18. It would be 12 pi over 18. So that's 13 pi over 18. x4 will be pi over 18 plus, add another 6 pi, so it would be, so did I screw something up? 18 pi over 18. That doesn't seem right, but it is. This will be 19 pi over 18. There's a lot of them. x5 is pi over 18 plus 24 pi over 18. I think we're getting closer to be done. This will be 25 pi over 18. X sub 6 will be pi over 18. I mean, you could just keep adding pi over 18 to the previous one, right? Maybe that would be easier than writing it all out like this. This is just getting ridiculous. Computationally in my brain, I don't like this method. Okay. But, you're going to get the same answer. It's just, so pi over 18 and then plus 6 pi over 18, right? So that would be 7 pi over 18. And then add in another 6 pi over 18. So that would be 13 pi over 18. And then 19 pi over 18. This is quicker. And then another 6 pi over 18 would be 25 pi over 18. And then another 6 is 31 pi over 18. And then another 6 is 37 pi over 18, which is bigger than 2 pi, so we're done. Okay, so these are your solutions in between 0 and 2 pi. Okay. Okay, so that really only happens when you have like this multiple angle type deal, like 3 times x or 4 times x. You have to worry about all of these additional angles. I will put one like that on the test. Okay. Anyways, let's look at these other problems. These, if you don't have that multiple angle issue, it's pretty simple for identifying the answers in between 0 and 2 pi. So again, this is on 0 to 2 pi. So let's look at this one. 2 cosine squared plus 3 cosine x equals -1. So these problems are quadratic form. You're going to want to set it equal to 0 and then factor it. So cosine x plus 3 cosine x plus 1 is 0. Factor it. We'll get 2 cosine x and then cosine x looks like plus 1 plus 1. And then you have 2 kind of equations to solve in the interval. 0 and then cosine of x plus 1 is 0. So here 2 cosine x is -1, cosine x is -1/2. So we just need the solutions in between 0 and 2 pi. You don't have to do anything fancy for this, like do the 2 pi ends. It's not necessary for these. So cosine, the reference angle is pi over 3. Cosine is negative in the second and third quadrant when x is, so this is 1 pi over 3, 2 pi over 3. Here's 3 pi over 3, and then this is 4 pi over 3. Okay. For the other one, where is cosine x equal to -1 in between 0 and 2 pi? That's just going to be at pi. So x equals pi, and these will be your answers. Okay. I mean, if you were to go about doing the infinite solution case, in this case you would end up with x. So just to convince you that you don't have to kind of do the infinite solution case here, your solutions would be x equals 2 pi over 3 plus 2 pi n, or x equals 4 pi over 3 plus 2 pi n. The deal is, you would get x equals 2 pi over 3, and then if you added in another 2 pi to that, you would get 8 pi over 3 for the next one, which is bigger than 2 pi, so you wouldn't include that one anyways. And then over here, you would have 4 pi over 3 plus 2 pi n is the same as 6 pi n over 3. So the next one would have been 10 pi over 3 when you add in 6 pi over 3 to 4 pi over 3. But again, that one's bigger than 2 pi, right? 6 pi over 3 is 2 pi over 3, so 10 pi over 3 is definitely bigger. And you're just left with these 2 solutions from that half of the problem, right? Which is what I have right here anyways. Okay. Well, the infinite solutions for cosine x equals -1 would be x equals pi plus 2 pi n, and the infinite solution kind of. So in that case, the first solution would be pi, and then the next solution would be pi plus 2 pi, which would be 3 pi, but that's bigger than 2 pi, so we would throw it out, and we're just left with this one. Okay. So in other words, those are our solutions. So any way you slice it, if you need to write out the infinite solutions, you're still going to end up with the same answers if you do it correctly. Okay. let's look at just two more. So this is number 59. Again, we're on the interval from 0 to 2 pi. We have sine x plus 2 sine x cosine x equals 0. This is basically kind of quadratic. You're just going to factor it. So sine x is 1 plus 2 cosine x is 0. And then you set each part equal to 0. Over here, on the unit circle, sine is 0 at 0 and pi. Okay, so x equals 0 and then pi. And then again at 2 pi, but then that's too big because we're on the interval from 0 to 2 pi, not including 2 pi. So you have that open parentheses on 2 pi. Okay. So the other guy is 2 cosine x equals -1. So cosine x equals -1/2 again. So those will be just the 2 pi over 3 and then your 4 pi over 3. Okay. And I'm only doing that quick because we just had the answer to that above. Okay, one last one, 71. So we have cosine. This one's a little harder because you kind of have to dig into the more obscure identities. But here, the deal is, I said in the lectures, you want everything in terms of the same trig function, or you want everything in terms of the same angle. So here on one side I have a 2x, on the other side I have an x. So I'm hoping to get everything in terms of just x and in one function. So if you go back to kind of our formula sheet, wherever that went, I think it's online. Look at cosine 2 theta. And yeah, it can be cosine squared, sine squared, but that I'm not going to like that identity because then not everything's in terms of cosines. So I go to the next one, 2 cosine squared minus 1. That works. Okay, so I'm going to replace cosine 2x with 2 cosine squared x minus 1 equals cosine x. And then everything's in the same angle. We have all the same trig functions, and it's quadratic. So I can set it equal to 0. Then factor it. So I got 2 cosine x, and then cosine x, and then what do we have? I need -1 here, and then +1 here. And then you got your 2 mini equations. Again, we got that guy. Sorry that this one isn't very interesting. -1/2, so we already have those answers. 4 pi over 3. And the other one was 2 pi over 3, so I put them in reverse order. Cosine x equals 1, and the unit circle, where does that happen? That happens at 0 and at 2 pi, but 2 pi isn't there, so just x equals 0. And those will be our 3 answers. Okay. Okay, so that's the degree. Expect those types of problems. Usually, if I don't cover it in my review, you won't see that sort of thing on the test. Expect that level of difficulty, so I'm not going to put anything more difficult than what you see here on the test. Expect problems from these question pools. So 5.5 problems, expect anything from 11 to 73. I won't be putting extremely hard problems on there, so if you see something that is just like, wow, that looks impossible, I probably won't put it on the test anyways. But that'll do it for us. Thanks for watching as usual, and we'll see you next time. No video quiz in the review videos, so okay, we'll see you next time.